So let's begin. Okay. So I think the microphone is on, the camera is on, and I'm going to use the whiteboard. It's a great pleasure to be here. And the topic of the lecture is financial frictions in macroeconomics. And I think that this is a really fantastic summer school, and I think that the whole it has a very unified focus, which is really awesome. And I think that I can build on some things, and Jose and Peter and I unfortunately missed Nobu's talk, but I'm sure that will also be helpful. Let me start by talking about some broad ideas. So one of the ideas of macro and financial frictions is basically about the role of the financial sector, and the fact that sometimes there can be crisis because of the whole financial system or the financial sector. So financial institutions, they do a number of useful things for the economy. So they channel funds for investments, and they identify good projects and lend money to firms. Financial institutions, they also improve risk sharing within the economy. So that's another function. Then they perform maturity and the liquidity transformation, so they create the assets which are more liquid. This literature that has been growing about macro and financial frictions is about the possibility that sometimes these functions could be impaired. Okay, and it's also about the spillovers into the real economy. So building upon some ideas, for example, from Peter's talk, that the intermediary capital is important. Okay, and from Peter's talk, intermediary capital is could be used to explain, for example, mispricing and arbitrage opportunities and risk premia. And so the most basic way to capture it is to have a model where the, let's say, intermediaries and households, okay, and what this interval represents is basically total wealth in the economy, okay, and so the intermediaries, they need some capital, some wealth in order to operate. Okay, and this is the households. Okay, and when when the intermediary's wealth share is too big, well, maybe this is not so good. So then, households could be undercapitalized, and households could be a bottleneck.
Who owns the intermediaries?
Huh?
Who owns the intermediaries?
Who are the intermediaries?
Who owns?
Who owns the intermediaries?
In other words, the capital disposal, is that owned by somebody else before?
So
Are they standalone entities?
The question is whether households' wealth do not include intermediaries' wealth, because they would own intermediaries.
Right. So the intermediaries, they could have some outside equity, and they could have some inside equity. So the bankers, that the managers of these intermediaries, they should have some skin in the game, and that's what I'm talking about as intermediary wealth. So the households, they could they could have a stake in the intermediaries, but that's just a way for intermediaries to share risk with the households. So I'm talking about the skin in the game that the intermediaries have. So
But the money that they get does not belong to the households in the end of the day.
some of it belongs to the households.
So you think about two classes of people in the end. You have the managers and the other households, right?
So let's.
Is that the way to think about managers and then the other households?
So here's the balance sheet of intermediaries, right? To answer this question, so there are some assets, basically loans, for example. Okay, and then there are some deposits. So these are liabilities. So households they own those. And there could be some, in different types of equity, there could be some inside equity. And then could be some outside equity. Okay, so
You're talking about the inside.
I'm talking about the inside equity as the intermediaries'
That's the
wealth
of the
share.
managers, in a sense, right? The
Yeah.
managers have the claim to the title.
So the households, for sure, they could own a part of it. So this can fluctuate. Okay, so banks suffer losses, for example, in crisis. This can fluctuate, and then the intermediaries they become undercapitalized, and this can create this compromises what the intermediaries can do. And yesterday, Peter was talking about that if the intermediary's wealth drops, then you have a rising risk premia. So, for example, risk premia go up. So there can be arbitrage opportunities, which are more obvious in this case. So prices become less efficient. Okay, so this is one thing that can happen in the financial markets. Okay, so then there could be spillovers into the real economy. So firms maybe they cannot roll over credit, and it's more expensive, to get insurance. You cannot. It's difficult to raise equity in public markets. If you have a startup, it's difficult to get funding. So then there could be various types of spillovers. Spillovers into real economy. Okay, so asset misallocation. Okay, investment maybe drops. Investment drops, and less efficient risk sharing. Okay, and less efficient risk sharing. Well, you may be higher unemployment risk. So all of those kinds of things. Okay, and so now if we take a step back and if you want to sort of like look at a macroeconomy as a whole system, right? So there are various types of crisis episodes that can happen, and we are interested in asking various types of questions. So If we are in a crisis, how long does it take to recover? That's one type of a question. So another type of a question is, how do we know, how likely a crisis is going to happen, given where we are? That's another type of a question. And then, development of a crisis, something happens, are we going to go there fast, or, we are going to go there slowly, and why? And things like resilience of the financial system. So, in normal times, can there be some fragility that can potentially build up? So we basically want to understand, the whole dynamics, both, in crisis and in normal times, and, the various probabilities of what can happen, okay? And okay. So let me talk a little bit about solution methodology and how it's related to various phenomena that we want to describe. Okay, so there is I guess present, and there's past, and there's a future. Okay, so when we are at present time, we end up in some situation. Maybe we end up in crisis. Maybe not. We are interested in basically how we get there. Okay, and how we get there is, well, in the past, people made certain investments. Maybe they suffered some losses, and that's how we got there. So the description of how we move from past to present. So if we talk about, for example, the intermediary's wealth share, so this is going to be the wealth distribution could be a state variable of this macroeconomy of this system. Okay, so basically we want to describe laws of motion of states. Okay, that describe the system. So, for example, so this intermediary's wealth share, I'm going to call it eta. So, for example, eta. Okay. So, but there could be some other things that you want to describe. So, for example, it could be that the asset composition is changing. So, maybe there's creation of some complicated derivatives, credit default swaps. So asset composition could be a part of it, but ultimately then there are some forward equations that describe, and there are stochastic equations that describe how the system can potentially move through the different states. Okay, and so so in economics you can have forward equations. In physics we also have forward equations. Okay, but what is harder, economics or physics? So economics, of course, is harder because economics, tries to study people and how do you predict what people are going to do, and the reason why,
Newton made that observation.
Exactly. So I'm not the first person who made this observation. Okay, so then we have to talk about the future, and how the future comes is basically through expectations. Okay, so so people, when they make decisions at present moment, what matters is not only what happened in the past and how we got there, but what people expect about the future. Okay, and that has to be a part of the solution. So if we talk about the law of motion of wealth distribution, these are going to be forward equations that go from the past to the present. And if we talk about value functions or prices, so these are forward-looking. So they depend on, prices depend on future cash flows. Prices depend on who is going to be the marginal buyer of the asset in the future. So basically, they're going to be backward equations. Okay. And that's why sometimes the physics intuition is not applicable to economics. So people say, well, crisis is like a domino effect. Okay, so then the dominoes, they're all lined up, right? So each domino is a person. Why did you get there in the first place, right? So whereas in physics, this is you expect that maybe things line up in a certain way and then become fragile. People, they don't want to be in a compromising position. So maybe domino effect is not a very good analogy. But if you talk about something like, well, a traffic jam, well, maybe that's a better analogy because the drivers, they're forward-looking and trying to avoid things, and so that may be something better. So there will prices, value functions. Okay, and something Peter was talking about, consumption, right? Okay, so people want to anticipate their future consumption, and that's going to, translate into risk premium. Okay. So value functions. This is basically dynamic programming. It's when you have complicated dynamic decisions. What matters is you look at your value function, and then you decide what kinds of decisions are made at present. So, and at present, certain decisions are made. So, for example, portfolio choice decisions, consumption, asset allocation. So, so let me talk about the present. Okay. So there actually will be two things. So, portfolio, consumption. So people have to take into account their expectations about asset prices, and people have to take into account risk premium. Okay. So what does it mean? So for example, if we are at a time when we are on the border of crisis, okay, so that means that with high probability the prices are going to fall through the floor. So then the risk premia are high, and then do you want to invest as well? Maybe not. Okay, maybe. So there could be vulture investors that are basically standing on the sidelines and waiting to pick up assets when they're particularly cheap. So this is related to basically these decisions at the present. They're related to the spillovers. Okay, so the asset misallocation investment. This is about the spillovers into the real economy. So this is one aspect of the present. Okay, and then another aspect of the present is, well, people they make these decisions. Okay, so endogenous risk and amplification. Okay, so this is probably something that Nobu talked about. Okay, so as a result of these decisions, so the future prices, they are functions of the state variable. Okay, so we have let's say this is the state variable. The price of capital is, let's say, Q. So Q is a function of eta. So because the price is a function of eta and the decisions, they affect how the wealth distribution evolves. Okay, so then the prices, they react to the wealth distribution as opposed to fundamentals, and that creates endogenous risk. And then amplification is when it's risk. So with leverage, when prices change, then this has a feedback loop on the wealth of investors, and then because of this feedback loop, risk goes up even further. Okay, so there are basically four things. There's the past, there's the future, and in the present there are two things. There are the individual decisions and how these decisions, they could potentially create extra risk. Okay. So so these are some broad ideas, and this is sort of a big picture thinking about how the whole system works. Okay, and now if you have a particular model, then you have to start filling in the boxes. So next, let me show a particular model and make some of these things more concrete. So suppose there are households. So it's going to be a heterogeneous agent model. There are households, and then the other class of agents, I'm going to call them experts. Okay, so and this model is going to capture the fact that the expert's net worth is going to affect the asset allocation and productivity of the whole economy. So the experts, they need to have enough wealth in order to undertake investments. So the assumption is going to be that there is some capital in the economy. So, and how capital evolves is some capital can be generated through investment. So this is new capital that's produced. And capital can, you can have some output from capital. And the assumption is going to be that the experts, they are more productive at using capital than households. So the experts, their output rate is going to be A. So actually, let me write down A minus iota. So iota is the rate of investment. So there's some output which capital produces, and then some of this output can be used to create new investment. And then the households, they have a lower output rate. So A lower bar is less than A. So this capital can be traded at some price, QT per unit. So this is the price of capital. So this is going to be determined somehow in equilibrium. It's not an exogenously given price. And the law of motion of QT is dq. So let's say it follows some type of a Brownian process with some drift and volatility. And one of the things that we are interested in is psi t. This is the fraction of capital held by experts. So because experts, they're more productive than households, we say that if psi equals 1, then this is efficient allocation of capital. Okay. So, so here, let me.
The loan market between households and experts.
Yes, there is.
When you say held by experts, when at the hands of experts, these will borrow from households.
Yeah, so they have to. Exactly, they have to borrow from households. So I'll make that clear in a few seconds. Yeah. No. That's. Thank you for asking the question. Always helps me. So let me, sort of like anticipating what we're gonna see in how we're gonna solve it. So, whenever you're trying to, write a model or solve a problem, it's always useful to make a guess of, how it's going to be. Sometimes your guess is right and sometimes your guess is wrong. And if it's wrong, then you always learn something. So, it's always good to make a guess rather than to be stuck, even if the guess is wrong. Okay, so on the horizontal axis, I'm going to put this eta, the expert's wealth share. And on the vertical axis, so, what do we expect? Well, when experts, they have enough wealth, they're going to hold all of the capital. And, how is that possible? Well, they have to borrow from households to hold it, because without borrowing, they can hold all the capital only if their wealth share is 1. Okay. So besides capital, which is, in fixed supply K, there's also going to be a risk-free asset in zero net supply. So this is the risk-free rate. Okay. So this is the fraction of capital held by experts. And at some point, because this capital is risky and the assumption is that the borrowing is risk-free, the experts, they will sell some of the capital to households. So even though households are less productive, the experts, they started suffering losses, and then they're going to be risk averse, so they want to pass on some of the risk to households. Bless you. So then basically it goes down, and this is 1. Okay. So the question is, well, how is this price of capital determined in equilibrium, and how is the capital allocated, and what are going to be the equilibrium dynamics? So the equilibrium dynamics is, well, when we start at the given point of the state space, what is the drift and volatility of the state variable? So as a function of the shocks, how the system is going to move around. If you call this the crisis region, and this is I think I'm gonna explain why this is a good interpretation. Okay, how often the system enters the crisis, and things like that. So we are interested in understanding those things. Okay, and so okay.
So here you might be ruling out equity participation, because you could solve that problem because households will simply lend the capital as an equity portion to the experts.
Mm-hmm.
To use their good technology, which is better than the households can do, and then pay a dividend back to share the surplus in some way.
Yeah. So exactly. So
There's no equity participation here. The only market is the bottom line is the
So yeah, exactly. So I'm going to assume that there is no equity issuance to make it easier to solve. Okay. So this also works if you assume that the experts, they can buy capital and issue some equity to households, but only up to a certain fraction. So they have to invest at least 20% of their own wealth, and so if we make an Yeah. Okay. Um, so okay. So let me start by I guess with number one. Okay. And I'm going to basically derive the law of motion of experts' wealth share. And in order to do it, I have to talk about asset pricing a little bit, and this is going to be easy for me because Peter already talked about asset pricing. So uh, so if we take any two assets, so this is expected return in asset A and expected return in asset B, then what explains the difference in returns? Well, it's if you look at the risk of these two assets, well, the difference in the risk should explain the difference in return. Okay. And specifically, what matters is the covariance of the difference in risk with the stochastic discount factor. Okay, and what is the stochastic discount factor here? So in this world, what's going to be different from a standard finance world is that households and experts, they're going to have different stochastic discount factors. Okay. So they have different investment opportunities. So the households, they can invest in capital and they get some return, which corresponds to this lower output rate. And the experts, they can invest in capital and they can get return, which corresponds to this higher discount rates. And because of that, their consumption paths will be different, and so their stochastic discount factors will be different. Okay, so we can use the expert stochastic discount factor to price the investment opportunities of experts, so capital with this output rate and the risk-free asset, and we can use the household's stochastic discount factor to price the investment opportunities of the household. Okay, and what is stochastic discount factor? Well, it's how correlated, I mean, you want to look at how correlated is any given risky asset to the marginal utility of consumption. So if it's an asset which pays which pays a lot when the marginal utility of consumption is low, because so then the risk premium is going to be higher. Okay. So stochastic discount factor, okay, so if we have, let's say, discount rate rho and some utility of consumption, so that's going to be the stochastic discount factor. It's the marginal utility of consumption discounted, right? And here we are interested in the volatility of the stochastic discount factor. So so I'm going to proceed assuming that the experts in households, they both have logarithmic utility, because this will make the calculations easier. And I'm going to assume that the households, they have discount rate rho underlined, and the experts have discount rate rho. And the assumption I have in mind is this, but okay, I'm going to explain in a moment why this is. So if utility is logarithmic, then marginal utility is 1 over c. Okay, and the volatility of stochastic discount factor. So let's say this is the stochastic discount factor. Okay, it's gonna be minus the risk rate dt plus So
when you write it like this, with the grid, but it comes back to feeling that it's short, you're choosing something about the probability where you choose something about probability, right?
yeah. So what will matter is, so this equation only has the volatility.
It doesn't matter, yeah.
So don't even. Okay. So what I want to say is, okay. So to make long story short, what matters is the volatility of marginal utility. So if the volatility is consumption is C, okay, then the SDF has volatility minus sigma C, because it's 1 over of a logarithmic utility, exactly, minus sigma C. And for a logarithmic utility, agent C equals rho times n, well, rho underlined times n if it's a household. So it's a fact that it's proportional to net worth. So this is equal to sigma n, and this is equal to minus sigma n. So in here I can put in minus sigma n, the minus and minus cancel out. So in the end, for a logarithmic utility agent, basically we have this this equation. Okay, so if an asset is more correlated with the wealth of the agent, then its expected return should be higher, because the agent cares less about consumption when his wealth and consumption go up. Okay. So all right. So I'm going to use this equation to derive the law of motion of eta, and I'm going to show two ways of doing it. Okay, and one way is going to be, more straightforward, and the second way is going to be super simple, and you're going to think that I'm cheating when I show it, but I'm going to show the first way first, so the answer is going to be the same, and therefore
You're convinced about it.
therefore you have to trust you can trust the second one. Okay, so all right. So how are we going to derive this law of motion? So the experts they hold some capital. Okay. This is the balance sheet of experts. This is their asset side, and this is their liability side. They have some inside equity. All of it is inside equity and some debt. Okay. The assumption is that it's a risk-free debt. Okay. And so what is the volatility of capital? Okay. So if we have k units of capital, which is priced at price Q, okay. So if you want to find the volatility of a product, so this many units is priced at this price, then Ito's formula tells us that the volatility of a product is sigma plus sigma Q. It's the sum of volatility. Okay. So if you've never seen it, then you can think about it intuitively. So this product can go up if K goes up, or if Q goes up. And if K can go up by 1% and Q can go up by 2%, then together they go up by 3%. And so we have to, we add up 1% and 2%, and that's the sum of the volatility. Right? Okay. So that's the volatility of this capital that the experts hold. And if we want to talk about the volatility of their wealth, okay, so then we have to take into account that they're levered, okay. And this is the volatility of capital that they hold. Now, what is their portfolio weight on capital? So they have some portfolio weight on capital and some portfolio weight on the risk-free asset. So the portfolio weight on capital is psi t over eta t. That's the portfolio weight on capital. Okay. So does it make sense? Well, this is the fraction of experts' wealth as the fraction of total wealth. And this is the fraction of total wealth that they hold in the form of capital. This is the fraction of capital that they hold. So this ratio is the portfolio weight. Okay. And if I multiply it by sigma plus sigma q, then this is going to be the volatility of wealth, call it sigma n, of experts. Okay. So so now suppose I want to write down the law of motion of the expert's wealth. Okay. So there are different ways how I could do it. So one way how I could do it is I could look at, okay, that there is a risk-free asset, and then there is capital, and what is the return on capital, so I can try to decompose it. What is the dividend yield on capital? What is the rate at which, Q is changing? What is the rate at which K is changing, which is that, so I can, go through that whole algebra, okay? And it turns out that it's going to be a lot of algebra, and it's very easy to start swimming in that algebra. Okay, so instead, here's another way how I can write down the law of motion of experts' wealth is I'm going to start. Okay, so the experts, they let me start with risk. I'm going to start with risk. So this is the risk that the experts are exposed to. Okay, and given this risk, what is their expected rate of return? Well, it has to be the risk-free rate plus the so the difference between the return on the whole portfolio of experts and the risk-free rate has to be explained by this formula. Okay, so this is so the difference between the risk-free rate and the return on the whole portfolio has to be explained by the difference in the risk of the whole portfolio minus the no risk, the risk-free rate, and times the risk, the price of risk, which is equal to the volatility of wealth. Okay. So this is the risk, and the return equals to the risk-free rate plus the risk premium, and the risk premium equals to this squared. Okay, so this is the return on the whole portfolio of an expert. So that's nice, right? That just if we know the volatility, then we can back out the risk premium. And this is for logarithmic utility. For other utility functions, it's a bit more complicated, but it's the same thing. And then out of this portfolio, so this part is not the whole picture because this is the total return, but the experts, they're also consuming out of their wealth. And how much they're consuming? Well, proportionately to rho times wealth. So to take into account the consumption, I just have to subtract rho. Okay.
But rho dx is rho. Rho dx is rho. The other one is rho bar.
Yeah, the expert is rho, the household is rho lower bar. Okay. So that's the law of motion for experts. Okay. And if I wrote this, and then if I ask you, well, what is it for households, then you know, you can do it by symmetry, right? So let's call it that for households, d n underlined over n underlined equals, so they hold this much capital. This is their net worth. The risk of capital is the same, plus the risk-free rate. And then they have to take, I guess, risk squared for households. So the households, they also have logarithmic utility, and they subtract rho underlined. Okay. So, all right. And so if we have the law of motion of, you know, the net worth of one group and the law of motion of net worth of another group, then we can find the law of motion of the wealth share. Okay. And how? Well, by using the right type of an ethos formula. So I'll show you one ethos formula which is useful for, you know, these purposes. So if you have the law of motion of something, so how do we, so eta equals to n over n plus n underlined. Okay, and the question is, well, what is going to be the law of motion of eta? Okay, so something that you could guess is the volatility of eta, right? So if we have the volatility of one part which has weight eta, and the volatility of another part which has weight 1 minus eta, then the volatility of this the weighted average, right? Oh, wait a minute. No. So I guess I could, right. So I guess let me show you the formula. Okay. And then I will explain it intuitively. I think that will be easier. Okay, so this is the formula. Okay, and
What you have there is the eta divided by 1 minus eta times eta. That's not the eta over eta.
so the formula gives the eta over 1 minus eta times eta, right? And this is just symmetry, right? This is just symmetry because one fraction is eta, one fraction is 1 minus eta, right? And this is just the the product of the two fractions. But I guess let me give you a little bit of intuition, not a whole lot. So if n has bigger drift, right, then this ratio is going to have a bigger drift, right? But there's one part in the numerator, and then there's part eta in the denominator. So after you take that into account, this has to be multiplied by 1 minus eta, and that's why 1 minus eta basically would be there. And this enters symmetrically, so this is exactly the same form, the difference in volatilities. And in eta's formula, there is always an extra drift term because of the volatility. So that's that term. Okay.
Or you could see DP instead of finding D over A, you find D of 1 over A. That it's only going to have an n bar over n.
Say it again.
If you look instead of d eta, you look d of 1 over eta. 1 over eta is just 1 plus n bar over n. And then you have, this is Vito's formula.
Right. So you could also do it. Yeah. Right. You could also do it that way. I mean, you could. Yeah. You could add those up and get the formula for the sum, and then use eta's formula for the ratio. But the reason I wanted to use this one is because I actually save at least one line on the whiteboard. But let me plug it in. So if I plug it in, then well, first of all, one thing that I can do right away is that I can multiply both sides by 1 minus eta, because I'm interested in d eta over eta. Okay, and then I can plug things in. So this is equal to so it's 1 minus eta, and this is going to be sigma n squared. Okay, this is going to be minus sigma n underlined squared, and this risk-free rate is going to cancel out, and this discount rate that's going to give an extra term, which I'm going to put at the well, I can put it. I can probably put it right away. Minus rho plus rho underline, right? So then I have another drift term, which is this, and then times minus the volatility of total wealth, which is sigma plus sigma q. So this is also equal to sigma plus sigma q. Okay, and I have so this is the drift, and I have sigma n minus sigma n underlined dz. This is the volatility. Okay, and then after this I can transform it a little bit, and after I transform it, what I'm going to get is minus okay, so basically this is the equation where what is sigma eta? So sigma eta is this part. So maybe I can get sigma eta directly from here. So this is sigma n, and eta is, do I have it written somewhere? Okay.
So have it there, n over n plus n pi. Eta is written there.
Oh, eta is written there, right? Which is also n over q times k, right? Which is also n over q times k. So this is, I know the volatility of n. I know the volatility of q times k, which is that. Okay. So therefore, sigma eta is the because it's the ratio, it's the difference in volatility. So that's going to be psi over eta, sigma plus sigma q, minus sigma q. Okay. And so that's the formula. Okay. And let me give you a little bit of intuition. Okay. So to give you a little bit of intuition, so one thing that we see is that when experts, they hold more capital than their net worth, then they take on this risk. They have to be compensated for this risk through the risk premium, right? And one of the things that we see is that the more risk they take, the more risk premium they earn. Also, the bigger the risk. So that's one part. So, and this is basically a term that helps the recovery from crisis. So if we end up somewhere here, then that's going to affect the speed of recovery, right? And then in any model where the two types of agents and one type is more productive than another, okay, the type that's more productive can sometimes save their way out of the constraints just because they earn more. And that's why this model assumes that the experts are less patient than households. So you can give some justifications for that why bankers are less patient, but it's a bit of a well, because they're more productive, supposedly. But because they're less patient, they consume, and so they don't overwhelm the whole economy. So that's that term. Okay. So that's one way of deriving it. So let me maybe derive it. I promise to derive it the fast way, another way. Okay. So let's see if I can do it. Okay. So
Here's a question. Can I ask a question?
Yeah.
So in your model, if you it's roll and roll bar, for certain values of roll and roll bar, you need big difference in productivity, so the bankers become the more wealthier guys in the house, right? So they either become well, you have a question how many bankers and so on. What's the unit here? Bankers are
so one of the questions so one of the things we can look at is we can actually look at the drift as a function of eta. And at this point, I'm going to run a little bit ahead of myself, but what's going to happen is that it's going to look something like this. Okay, so this is let's say mu eta times eta, and this is a function of this is eta on the horizontal axis. So there is going to be a crisis region where it's going to turn out that the volatility is high, and because of that, the risk premia are high, and the risk premia actually help recover from the crisis. So this increased risk also makes it likely that we're going to go much deeper into the crisis because of the shock, right? But the the expected rate of recovery, it would predict fast. And then so we see that the drift is positive, and then somewhere the drift is negative. So the drift is positive because of the difference between A and A underlined, and the drift is negative because of the difference in the discount rate. So if the discount rates were the same, then the drift would always be positive.
That gives a stationarity on the rate.
Right, exactly. So that's yeah. So that's about the ratio of the bankers. Okay. So let me show another way of deriving the same thing, and you're going to think that I'm cheating. So I'm going to look at this equation, and I'm going to say that, well, you can measure returns and you can use any numerator basically. So you can use output as a numerator. So I just used output, but you can use this pricing equation. You can change to dollars, to euros, to to any numerator. Okay. And what numerator am I going to use for this equation? Well, I'm going to use the numerator to be the wealth of the whole world. Okay. So numerator the numerator is world wealth, and then I'm going to apply this equation, and one of the assets is going to be maybe I can do it even simpler, but okay. So one of the assets is going to be the portfolio of experts, and another asset is going to be the risk-free asset. Okay. So what is the return on the portfolio of experts when the numerator is world wealth? So I'm going to claim that the return on the portfolio of experts when the numerator is world wealth is rho plus mu eta. Okay. And why that's the case? Because mu eta is the capital gains rate of the wealth of experts, which in those units are just eta. And rho is the dividend yield because the experts are consuming out of their portfolio at rate rho. Okay. So that's the return on the experts' wealth in that numerator. The return on the risk-free asset is some return, r hat f. Okay. So some number because we changed the numerator, that's not going to be rf, but it's going to be something else. And then on the other side is basically the difference in risk. Okay. So it's the difference in risk between the expert's wealth and the risk-free asset. So, and it turns out that the numerator is, of course, going to affect the risk of the asset. So the risk of the risk-free asset is no longer going to be risk-free. Okay, because we are measuring the return on the risk-free asset in terms of a risky numerator. Okay, so the dollar has a risk-free return in the dollar, but not a risk-free return in the euro. But it turns out that the difference in risk does not depend on numerator. Okay, so for the difference in risk between it doesn't depend on the numerator, and and the difference in risk between the expert's wealth and the risk-free asset is just going to be that which was the same. It's the same before the change in the numerator as after the change in the numerator, and so that's going to be psi over eta sigma plus sigma q. Okay. And what about the risk premium? So that's the volatility of wealth of experts in the new numerator, which is sigma eta. Okay. So basically, we have this equation, and then if I write the same equation for households, so for households, this is going to be a rho minus eta mu eta divided by 1 minus eta minus rf hat. So this is the drift of 1 minus eta. And the way to see it is because the drift of the whole wealth is 0, and the weighted average of these is, you can see, is 0. Okay. And this is equal to 1 minus psi over 1 minus eta sigma plus sigma q, which is the the same term for households, and then the last term is minus eta sigma eta divided by 1 minus eta. Okay, and so that's the pricing equation for households. And now we can basically subtract one equation from another. And right away we get the drift of eta. So basically that's going to give exactly the same way, the same expression. But this is a much more efficient way of doing it. But you have to do it carefully. But sometimes changing the right numerator significantly speeds things up. Okay. So right, okay. So this is only one part, okay? And let me do now, these two parts, okay? So one of the parts is the allocation of assets, and then the second part is endogenous risk. Okay, so so the allocation of assets, okay. So what's the return on capital? So the return on capital is basically the dividend yield, which is the output minus, so the net output divided by the price of capital, plus the capital gains rate, which is dq times k over q times k. And this is the return on capital that the experts earn. So this return on capital minus the risk-free rate has to equal to the difference in the risk of capital, which and the risk-free asset, which is sigma plus sigma q, and the volatility of sigma n, which is psi over eta times sigma plus sigma q. And
by the second term of the load, here
mm-hmm.
you have a price, and you say what is the price ratio, fine.
Yeah.
Then you should have the change in price.
So this is the capital gains rate, right? So this is the change in the value of the asset divided by the value. I think I have to do. Sorry, I have to do the expectation, right? This is it.
Okay, so why isn't the expected value? Because the capital itself can benefit stochastic rate. Right?
Okay. Yeah.
That has to do with the fact that you have to depreciate the random rate.
So this is the equation for experts, and for households, it's the same equation except A gets replaced with A underlined, and the risk of capital is the same. The risk premium is going to be the risk premium. And instead of equality, we are going to have an inequality like this. So sometimes the actual return could be less than the required return. That's in the region when households, they do not hold any capital. And so this is going to be equal if psi is less than 1. Okay. So I have these two equations, and these two equations, if I subtract them, then I'm going to get A minus A underlined divided by Q equals psi over eta plus 1 minus psi over, sorry, I think I have to subtract, right? Minus 1 minus psi over 1 minus eta times sigma plus sigma Q squared. Okay. So this is the allocation equation that determines psi when psi is less than 1. Okay. And another part of the allocation, what happens at the given moment of time, is the allocation of consumption, right? So the total output is A minus investment, and this is equal to the supply of consumption. So this actually times, well, no, so I did this wrong, because the total output is fraction psi is held by households, fraction 1 minus psi is, sorry, psi is held by experts, 1 minus psi held by households. This is investment, so this is total supply of consumption, and total demand equals to the wealth, which is Q times K. So if I multiply this by K, this is supply. This Q is the wealth, and I have to multiply this by the discount rate, because the consumption is proportional to the discount rate times wealth. So basically, this is demand. So this is supply, and this is demand. Okay. And then what else do we have? So this is these equations. They are the allocation of capital and the allocation of consumption. So the last equation I'm going to write is the generation of endogenous risk. So so endogenous risk comes from the fact that the price of capital is a function of eta. Okay, and eta has some volatility. So when the experts, when they suffer losses and eta goes down, then Q is also going to go down. I mean, there is intuition, but the intuition is that so it's actually not related positively to eta on the whole range, but it's related positively to eta in the range when households hold some capital. Yeah. So in this range, as we go from here to here, then total output is going up, and total output is going up means that the price of capital is also going up. So in other words, the whole economy, when eta goes down, the whole economy becomes less productive. Okay. So here I can write down ethos formula. So sigma Q equals, using ethos formula, 2 Q prime of eta over, so I'll write it like this, Q of eta times sigma Q. So that's the absolute volatility of Q is equal to Q prime times the volatility of eta, which is psi minus eta over eta, sigma plus sigma Q. This is equal to sigma eta. Oh, sorry, I did this wrong. it's sigma eta times eta. Yeah, so that's the formula. Okay. So now it looks like we are in the woods and there is no light ahead. But we are actually basically done. Now let me explain why is it that we are basically done. Okay. So we have the law of motion of eta, and something that we can do now is, in order to describe the whole system dynamics, what do we need? Well, we need psi, and we need sigma q as functions of eta, right? And if we so let me basically try to determine those. Okay. So this is eta on the horizontal axis. Okay. So what I'm going to do is I'm going to solve for q as a function of eta, and also psi as a function of eta, and sigma q as a function of eta. Okay, things that can be plugged into that equation. And I'm going to show that these three equations, they can be used to construct a first order differential equation for q of eta. So a first order differential equation is given eta and q of eta, it gives us q prime of eta. Okay. And if you want to solve this first order differential equation, we need one boundary condition. So for a second order differential equation, the one that Jose was talking about, you need two boundary conditions. Here you need only one. And one boundary condition is here, if I plug in eta equal to 0, right, then what I'm going to have is I'm going to have, so psi is equal to 0 when eta is equal to 0, because there are no experts, there are only households. So A underlined minus, so investment is actually a function of Q, is equal to Q of 0 times rho underlined. Okay, and this equation, and this is I have Q of 0. So Q of 0 is the fixed point of this equation. Okay. And how can we solve this system is, okay, so we start from eta and Q of eta, and let's stare at it quickly and see which equation we can use. So we can use, it turns out, this equation. So let me call this equation A, because I already have 1, 2, 3 over there. And how can we use it is, well, we know the point is from eta and Q to get the derivative. Okay, so we imagine that we are solving this system at a particular point. We have Q of eta, and then we are trying to determine the derivative so that we can take the next step and solve the whole system. So from this equation, we can we know Q, we know eta, we can get psi. So we can use equation A to get psi. And we can use the next equation, which is going to be this equation, call it equation B. And what can we get from it? So we know psi because we just found it, we know Q, and we can find sigma Q. And sigma Q is useful because, well, it's going to tell us, it's going to enter the dynamics also. So we get sigma Q. And then after sigma Q, then we get Q prime. We have one equation left, so we have to use it because that's the only thing that we have left. And in this equation, we have sigma Q we know, psi we know, so we can solve for Q prime. And as we do it, we are solving for psi, and when psi reaches 1, then we get to the end of the crisis region. And after psi is equal to 1, then I can plug in psi equal to 1 into this equation, and this equation can be solved for Q. Okay. So just like at this point. Okay, and then once we have Q, then we can get the other stuff as well using these. Well, this equation disappears. This equation only is for psi less than 1, but this equation is also true for after psi reaches 1. Okay, and then if we have Q, then we have Q prime, and then we can psi is equal to 1, so we can solve it for sigma Q, so everything can be solved. Okay. So now let me basically let's see what happens. So there is a crisis region where the price of capital drops, and it drops because the experts, they sell capital to households, and capital becomes less productive. And in this,
The price of capital is smaller, right?
the price of capital
Dropping depends on the movement of eta.
right. So yeah, exactly. So if eta drops, then price of capital drops. Yes. Yeah, the price of capital is smaller. So here the price goes down when there is a bad shock to eta, and goes up when there is a positive shock to eta. Okay, and this creates this is endogenous risk, and because experts are levered, this is going to lead to amplification. So I can disentangle amplification a little bit. So basically that's the solution. Let me. I have a couple of minutes left. Let me talk about a couple of other cool things that you can get. So I'm going to follow José's lead and try to do some comparative statics. Okay. So I'm going to try to do some comparative statics on sigma. Okay. And I'm going to do a little bit of a different trick. I guess it's also a version of, it also can be called comparison principle. But if you have two ordinary differential equations, first order, ODE1 and ODE2, and they're such that for any eta and q, ODE2 gives q prime, which is higher than ODE1. Okay, so suppose you have that property of these two equations. Okay, so then starting from any point, right? One of them has a higher slope than another. One solution. So this is the solution 2, and this is solution 1. Okay, and one of them is going to remain above another because they cannot cross back. Because if they cross back, then at the crossing point the slopes get reversed. Okay, so basically, if I have two equations and they satisfy this property, then so now I'm going to do comparative static on sigma. Okay, so consider sigma 1 and sigma 2, and sigma 2 is bigger than well, no, I'm gonna do this. Well, I'm gonna. Okay. I'm going to do sigma 2 and then sigma 1, and which one of them going to be bigger? I think yes, sigma 1 is going to be bigger than sigma 2. Okay. So suppose that's the case. Okay. So then let's compare two systems. Okay. So we have eta and q of eta, and then we have in the first step we are finding psi, in the second step, we are finding sigma q. Actually, so, and then in the third step, we are finding q prime. Okay, so let's just look at these two equations. So this equation, unfortunately, a part of it is hidden, but we start from A. But one thing that you can see is that sigma doesn't enter this equation. This is the market clearing condition, and so the two equations, 1 and 2, are going to lead to the same psi. Okay. So the second step is we are using equation B, and if you have the same psi, then something that we see immediately is that sigma plus sigma q is going to be the same. So sigma 1 plus sigma q and sigma 2 plus sigma q, they're the same. Okay. But because sigma 1 is bigger, it means that sigma 1 is going to be, sigma 1 q is going to be less than sigma 2 q. Okay.
Something missing your sigma 1 to sigma 2 sigma 1 to sigma 1.
Yeah, no, that's okay. Right. And then the last equation is this equation. So sigma plus sigma q is the same. Sigma q is different. Psi is the same. So q prime is going to be bigger when sigma q is bigger. So q prime of eta is bigger here than, no, other way, than q2 of eta. Okay. And then so what does it mean? It means that if we plot, well, I'm going to put the prime there. This is one in the first. Okay. And then if you plot the two solutions, then it's just like in here that one is going to be flatter than 2 because the slope 1 is flatter than slope 2. Okay, and so basically for a higher level of risk, the crisis region is going to be bigger than for a lower level of risk. So that's fairly intuitive, right? Since I'm sort of running out of time, let me just give you, one fact without a proof, which is cool, and maybe I talk about it next time. And after that, one homework problem. Okay. So the one fact without a proof is that one question we can ask is, well, what happens when sigma goes to 0? Okay. And it turns out that if you plug in sigma equal to 0 into the system, so we are interested in what happens in the limit as sigma goes to 0. If you plug in sigma equal to 0 into the system, then what do we have? We basically have a meaningful equation for psi. Okay. Then we have this equation, which with sigma equal to 0 gives us sigma q, which is some number, and then we plug it into here, and then we can get q prime. So one of the things that we can get from this exercise is that the limit sigma go to 0, there is still going to be a positive crisis region. Okay, and that's a cool result because there is basically there's going to be a crisis with self-generated endogenous risk. Okay, so last thing. So if you want to do your own exercise using these methods, here's a similar setting which you can solve in closed form. And you can try this at home. So here's an exercise. So this is also going to be a model with two types of agents, except that I'm going to call one group optimists and another group pessimists. Okay, and they differ in the belief about the law of motion of capital. So the optimists, so how capital evolves. So pessimists, they think that it's G underline dt plus sigma dz. And optimists think that it's G dt plus sigma dz. So capital is basically a Lucas tree, and the output is the same. So same for pessimists and optimists. Okay. So they only differ in the belief, and so I'm going to put here Z underlined. So the pessimists think that this is a Brownian motion, and the optimists think that this is a Brownian motion. So there's no investment to keep things simple, and the output is the same whether capital is held by pessimists and optimists. Okay, and the question is, well, what happens in equilibrium here? And here's an assumption. So you assume. So this is a parameter assumption. Okay, and here's a list of questions. So the first question is to get psi of eta. So you can obtain it in closed form. And then 2 is to obtain an expression for the risk-free rate. And then 3 is to obtain the volatility of eta. So in this setting, just like in that other setting, there's going to be a region where only optimists hold the capital, and if optimists they lose wealth, then there's going to be a region where pessimists hold some capital and optimists they hold some capital. And then the question number 4 is what is the drift of eta from the point of view of pessimists and optimists. So because the two groups, they have different beliefs about what is a Brownian motion. So likewise, the optimists are going to think that eventually they're going to take over the economy, and the pessimists are going to die away. And the pessimists, they're optimistic about their survival. They think that they're going to survive, and optimists are not going to survive. Okay. So, and to get you jump started, so the first step, of course, is what is the market clearing condition. So the market clearing condition, this is the output. So the discount rate is the same, log utility. And the market clearing condition is A equal to rho times Q. Therefore, Q is a constant, A over rho. So that's what's going to happen. Okay, so you can try this. This is a very neat exercise. Yeah. Sorry, I ran over time, but you can ask me. Yeah.
I suggest that since you're running out of time, we'll let people.
Or you can ask me. You can ask me. Yeah. So you can. So if this is the truth, then you have one answer. If this is the truth, then you have another answer. Mm-hmm. Yeah. Thank you.